Hi, this is once again Alex. This is a joint work with Daniel Gnad and Peter Jonsson, and I'm going to talk about complexity results for some cases of numeric planning. So, as we have seen before, in our case, numeric planning is just classical planning that is enriched with numbers. So we have classical variables with finite domains and numeric variables that have numeric domains and can be infinite, and that's the problem in terms of complexity. Actions, once again, have classical preconditions and numeric preconditions, also classical effects and numeric effects. The initial state is the assignment over all variables. Goal conditions can be classical or can have numeric conditions. So in numeric planning, numeric conditions are usually presented as linear formulas. In our case, we'll concentrate on what is called simple numeric planning, which means that effects in our case are not linear formulas, but instead constants. So each variable, each action can either increase or decrease variables by some constant. Note also that the number condition in the task representation is finite. We will need this for the next slide. So we will concentrate on restricted tasks. In restricted tasks, we would like to convert all linear conditions into conditions on some auxiliary variables. So each linear formula will be represented via numeric variable. When the action adds or reduces some constants to the original variables, we also update the auxiliary variable according to its formula. Note that its formula, if you add their constants, it's still a constant, so we still in single planning. The initialization is done, we just assign the value of the formula in the initial state, and what we got is the result. Now we can represent our task as intervals, like our conditions are basically intervals on variables, right? We need to check whether these variables belong to this interval. The interval can be compact, which means it's bounded and closed. It can go to minus infinity, can go to infinity. Usually we'd assume if there is no condition on the numeric variable, this means that the condition is just it belongs to the whole interval from minus infinity to infinity. And our goal in the future, what we're going to do is to bound those intervals. That's what we want to do, to make them all finite. And if those intervals are finite, basically our task is decidable on existence. So next, we need to mush our task a little bit more. We'd like to move to the integer form of the task. So instead of adding half or checking whether the variable belongs to 0.5 to interval 0.5 to 0.7, we would like all those numbers to be integers. How we do that? We just take all variables that are involved with all numbers that are involved with some variable, multiply them by their GCD, greatest common divisor, and basically get integers. We'd also like to, this is done via linear transformation. So we also would like our initial value of all variables to be 0. This can be done just by shifting everything by the initial state. And we would just, for simplicity, all goal conditions to be positive. If they're negative, multiply them by -1. If 0 belongs to the interval, the task is already solvable for this variable, so we are good. So starting from now, our tasks are have numerical conditions of the form integer numeric variable belongs to some integer interval with integer bounds. Still, those intervals can include minus and plus infinity. Okay, so the first lemma is as follows. If all our intervals are compact, which means nothing goes to infinity, our all search space is finite, and if it is finite, the plan existence is decidable. Moreover, if we can bound the number of bits on each interval, on the numbers that represent each interval, by the Savage theorem, we land in p-space, which is nice. Basically, the bounded integers programming is still, integer planning is still in p-space. So, okay, next, how we bring our problems to be bound. And that's the lemma that we're going to use quite a lot, at least in the paper. So suppose you have two numbers, A and B. And suppose you have a sequence of numbers that lead you from A to B. We take the maximal of those numbers in the absolute value. And we say as follows. If both A and B belong to the interval of 2 Cmax, then we can rearrange the addition of those Ci's in such a way that all the points will still be within this interval. We need this in the future to rearrange plans to be bounded by some interval. So let's look at the graphical example for this. So suppose you have the interval of 2 Cmax, you have A, you have B, and you have numbers that lead you from A to B. Say red lines are negative numbers and green and blue lines are negative. So in our case, this interval will be twice the length of the red line. So we start at A. And now the observation is as follows. Since this is the interval is at 2 Cmax length, we can always either move to the left or to the right, which means we can either add a positive number without exceeding the bounds or add a negative number without exceeding the positive bounds. If we have all our numbers either positive or negatives, this means there is only one line, no matter what you apply, that leads you from the current point to B. And this means that all points along this line still within the interval, if your original point within the interval. So here, green line will exceed the interval. So let's take the red one once again. Now, if we apply once again the red one, we'll exceed the interval. So we apply the green one. Once again, we cannot apply the green one. We apply the red one. We repeat the process until we get back to B and all our points within this interval. So that's what we're going to use to bound the state spaces of our future problems. Obviously, we cannot solve all numeric problems, but we will use this method to bound some of them. Let's start with the basic problem when we have no propositional variables and only one numeric variable. So if all our conditions are bounded, we are good. If not, let's move to the plan that exceeds the bounds, go somewhere towards minus infinity, doesn't reach minus infinity, and goes back. We take the bound of the variable. We take 2k we rearrange our plan, this part of the plan, so it won't go somewhere towards minus infinity, but will lie between WV minus, which is the minimal number that appears in the representation of the task, and 2K, which basically the maximum of the absolute values of the effects. We rearrange this so the plan will still be within those bounds. We do for the part that exceeds the WK plus, WV plus from above. Once again, rearrange it so that it will fit within these bounds, and we get a solvable task because now we have a finite search space. Once again, we can show that the search space is finite, and therefore the problem is finite. It is pseudo-polynomial because all the constants here are bound by n, which is the size of the task. Okay, let's expand this and see if we can say something more on the tasks that have some specific causal graph structures. Those are causal graphs, 4 causal graphs defined by Katz and Domschlag. Note that since we work with restricted tasks and all our conditions on numeric variables involve only one numeric variables, the causal graph defined exactly as in classical planning. This is not true for general linear tasks or even simple linear tasks, only for restricted tasks. But simple tasks can be brought to the form of restricted tasks, so this is a good part. So our claim goes about forks and actually general numeric leaves, but we will talk about this structure. So suppose we have an upper variable, we have 2 variables, upper variable is propositional, lower variable is numeric. All actions that affect the propositional variable can have only propositional conditions by the structure of the causal graph. So if we have such task, it is still decidable. Actually, it is pseudo-polynomial, but we won't go into that. So how it's done? We take the propositional variable, we go over all its variables, and for each one, for the variables, we defined strongly connected components if you can reach the variable x from variable y and vice versa. After we defined all strongly connected components, we start to enumerate path on those strongly connected components. By the structure of the graph, it means like this path doesn't really affected by the numeric variable. It affects the numeric variable, but doesn't affect the numeric variable. For each such a path, we use the dense round center lemma and compute the bound using an ILP because we moved to integer problems. Once again, we have an exponential number of integer linear programs. For each of those problems, we solve the bound. We search for the bound. If the bound exists, nice. If the bound doesn't exist, the problem is unsolvable, we move on. And then we take the maximal bound. Once again, after we computed the maximal bound on those, we take the maximum bound on x, and we have a bounded search space, which once again makes the plan existing problem decidable. Then we extend those results to forks with numeric leaves. If we have forks with numeric leaves, we can actually take a causal graph that has numeric leaves. Numeric leaves means that there are no names from numeric. We can merge all propositional variables into one large variable and still make the search space finite. If we have a fixed number of those propositional variables, we can show that our problem is actually lies in P space. That were the results. Now future work. We would like to know complexity of the roots. Actually, I think we already have a proof for that. We would like to prove that Planck's instants for DAG, directed cyclic RTs, are decidable. DAG means the causal graph. Once again, I think we can prove it. And lastly, it would be nice to show what is the minimal number of variables and what the structure they should have to make the task undecidable. If we have those, we have basically the full classification of RTs according to their causal graphs, which is nice. Thank you, and I would like to answer questions. Okay.